examples of graphing quadratics. So this first problem, we have something in vertex form. So to graph a quadratic, we're going to want to include some specific points, one of which is the vertex, try to identify a y-intercept. We'll get our axis of symmetry. We'll use the symmetry of the parabola itself to get a nice accurate picture of this thing. To start, let's identify what transformations have happened. So transformations. First, vertical. We're going to see we have vertical stretch by 2. We have down 3. And then in terms of horizontal, so we'll say the vertical transformations are there. Horizontal, we have left 2. So the vertex, we know we can identify by just looking at the translations that have occurred. So if I go left 2, down 3, from my parent function location of 0, 0, my vertex is now at -2, -3. And if my vertex is at -2, -3, I know my axis of symmetry is going to be at x equals -2, since it passes through that vertex. When it comes to a y-intercept, we can plug in 0 for x, and when I do that, we're going to get the following evaluation, where it's going to be 0 plus 2 is 2, square it, it's 4, times 2 is 8, minus 3 is 5. So the y-intercept is at 5. So let's plot those points. We'll draw in our axis of symmetry as well. So we have -2, -3. We have a y-intercept at 5. We have an axis of symmetry that passes through that vertex. Using the symmetric nature of a parabola, I also want to determine, does this open up or down? Now, because no vertical reflection has occurred and this parent function opens up, I know that it still opens up. So let's keep that in mind. Leveraging symmetry, this y-intercept is 2 units away from my axis of symmetry, so 2 units to the left of the axis of symmetry should also have a point. Let's evaluate the function at another point and then use symmetry to get our 5th point. So if I plug in -1, so f of -1 will be 2, -1 plus 2 squared minus 3, which equals -1 plus 2 is 1, square it is 1, times 2 is 2, minus 3 is -1. So the point -1, -1 is also on our graph. So let's plot that point. Using symmetry, if that point is 1 away from the axis of symmetry, then 1 unit away in the other direction is also a point. And now I can connect these. I have 5 points. That is enough to see the picture of the graph. Let's add in some other details that we may be asked, just so you can see domain of this picture. There's no restrictions on the domain of the quadratic. The range, lowest point, -3, up to infinity. -3 is included in that set, and there's your range. So that's the first example. Second example, still looking at vertex form problems. Let's identify the transformations. So vertical transformations, we're going to have reflect over x and then up 1. When it comes to the horizontal transformations, we will have right 3. We can identify vertex through the translations. So if I start at 0, 0 at the parent and I move right 3 up 1, I am now at 3, 1. That gives me the axis of symmetry location of x equals 3. We know this opens down because of that reflection over x, so we can add that in. So opens down. And let's add in one extra feature that we did not talk about in the last problem, was if we open down, we know we have a maximum point. So before, if it opened up, we had a minimum point. Let's find the y-intercept. Y-intercept can be found by plugging in 0 for x. Negative 3 squared is positive 9 times negative 1 is negative 9 plus 1 is negative 8. So let's plot some of those points. The vertex is at 3, 1. We have a y-intercept at negative 8. Let's add in our axis of symmetry. Let's use our knowledge of symmetry for parabolas to add in a third point. That y-intercept is 3 units away from the axis of symmetry, so we have another point 3 units to the other side. Let's evaluate the function at another point to get our fourth. Let's do f of 1. Choose easy numbers. So f of 1 means plug in 1 for x. We're going to get negative 2 squared, which is positive 4, times negative 1 is negative 4, plus 1 is negative 3. So the coordinate negative 1, negative 3 is on our graph. Or sorry, positive 1, negative 3. Using symmetry, get another point. And there's our 5 points that we need to get a nice accurate picture. Let's add in domain and range. Domain, this spans the entire x-axis. All inputs are valid, so negative infinity to infinity. Range extends down forever, and the outputs go as high as 1, included. There's your domain and your range. Moving on to some standard form problems. Standard form, sometimes it's helpful to identify A, B, and C. And again, with standard form, it's not easy to identify transformations, so we won't do that for these two problems. But A, B, and C, so based on my standard form, A is negative 2, B is negative 4, and C, there isn't one, so we say it's 0. Let's do A. Does this graph open up or down? Or say it opens up or down, so because A is negative, it opens down. Let's look at the axis of symmetry. The reason I'm doing that first is because this has a formula, and then from there I can find the vertex, as opposed to the other way around when we had vertex form. So the axis of symmetry is found by doing x equals negative b over 2a. So negative of the b over 2 times the value of a. Negative of a negative makes a positive. We have negative 1. X equals negative 1 is my axis of symmetry. That's going to help me out with my vertex, because the relationship is the axis of symmetry value is equivalent to the x coordinate of my vertex. So it's at negative 1. To find the corresponding y coordinate, we're going to evaluate the function at negative 1. So let's do that work off to the side here. F of negative 1, plug in negative 1 to x. Negative 1 squared is positive 1 times negative 2 is negative 2 plus 4 is positive 2. So we're going to have a vertex at negative 1, 2. Do we have a max or a min? In this case, because it opens down, we're going to have a maximum at x equals negative 1. Because again, the location is the x coordinate of our vertex, and the value of the max or minimum of the function is whatever the y coordinate for that vertex is. So it's whatever the output of the function is where the max or min occurred. So the maximum value is equal to 2. Let's look at y-intercept. Y-intercept is when the x coordinate is 0. If I plug in 0 to that equation, it all goes away. And again, as we discussed in class, it's equal to whatever the c value is to make life easy. So my y-intercept is 0. Let's plot this information. Y-intercept at 0. We have a vertex at negative 1, 2. Our axis of symmetry should pass through that vertex. Let's use symmetry to get another point. Let's plug in another point to get our fourth. So we're going to evaluate the function. Let's choose something easy. Let's use 1. So it's f of 1. We'll do that below. So f of 1 is going to be negative 2 times 1 squared minus 4 times 1. So I'm just plugging in 1 for x. 1 squared is 1 times negative 2 is negative 2 minus 4 is negative 6. So 1, negative 6 is a point. Use symmetry to get another point, and there are 5 points. Let's include domain and range. Domain, all real numbers. Range, negative infinity up to 2. And there's a problem with a standard form quadratic. And last one. A is equal to 1, B is equal to negative 3, C is equal to 2. Opens up because A is positive. The axis of symmetry is going to be equal to negative B so negative of negative 3 over 2 times A, which is 3/2. The vertex is going to be 3/2 f of 3/2. So we have to figure out, well, what's f of 3/2? To get that y coordinate, we plug in 3/2 to our function. So a little fraction work here. We have 9/4 when I square 3/2 minus 9/2 plus 2. To combine all these, we'll need common denominators, so let's keep it over 4. We're going to get negative 9 over 4 plus 8 over 4 is negative 1 over 4. So the vertex, 3/2, negative 1/4. We're going to have a minimum value at x equals 3/2. That value is equal to negative 1/4. So the smallest value this function outputs is negative 1/4. That's what that minimum is telling you. The lowest value this function will output is negative 1/4, and it occurs when x is 3/2. Let's do the y-intercept. It's whatever our c value is, or when x is equal to 0, which is 2. Let's plot some points. So the vertex, we got 3/2, which is 1.5, and then negative 1/4. So somewhere in there, we got 2. We got an axis of symmetry running through that vertex that we'll add into our graph. Draw a better line. Plot our third point using symmetry. So that y-intercept is 1.5 units away from our axis of symmetry. So another point 1.5 away would work. I can plug in other points to get my fourth. The point I'll choose, let's compute something easy, right? Let's make our life easy. So f of 1 is a good choice. So when x is 1, what is the y? We're going to get 1 minus 3 plus 2, which is 0. So 1, 0. So half unit away, so another half unit away is at 2, 0. And we're going to get some picture that looks like this. We add in domain and range. Domain, still all real numbers. There's no application or context that would restrict that. In range, the lowest value it goes is that lowest output value associated with the minimum, which is negative 1/4. and it goes up forever. So that will conclude the video on graphing quadratics, examples that include both vertex form and standard form